Welcome, ladies and gentlemen. May I have your attention, please? Thank you. Raise your hand if you didn't get a red mark for today. Today, the 16th. You good? 16th? Okay, let's go ahead and practice with our function composition. So, recall, we can find a simplified equation for the composition f of g of x, particularly if we rewrite it in this nested notation. So, if I rewrite f of g of x, in function notation, instead of the composition symbol, then it's easy to see what my inner function is. So my inner function there, g of x, is going to be stuffed into my outer function's rule. F's rule everywhere f accepts input. So we can go ahead and rewrite that. F's rule is 3 times input minus 4. Except everywhere I see an input, I'm not going to put x, I'm going to put g of x in its entirety. So I'm going to put g of x squared minus 1, I'm going to put that into f's rule. So we'll put the x squared minus 1 right there. And then we'll go ahead and simplify this if possible. It looks to me like we can take this outside factor and multiply it through the sum or difference inside the parentheses in accordance with distributive property. And then combine like terms last. So I'm getting 3x squared minus 7 for my final. Raise your hand if you already had that. Did we get all the way to the end? You did? That's great work. Thank you. Hands down. Nice work. I'll box that. And then I did make a little bit more space on subsequent slides. So we'll continue on with the same problems, but we'll use a little bit more space. This time we're going to evaluate a function with numerical input for our composition. And so when we plug in a value, right, into our composition, we should expect to get a value at the final answer as opposed to a function, right, the algebraic expression. So let's go ahead and take a look what happens. H of f of 0, I'm going to go to my h function, and I'm going to plug in f of 0. In order to find f of 0, I need to go to f's rule. F's rule is 3 times input minus 4. But instead of putting input x into f, I'm going to put 0, my x value concerned. Right, I'm going to put 0 into my function f and work from the inside out. So here we go. 0 goes into f's rule. 3 times 0 is 0. Minus 4 is negative 4. So this is h of negative 4. How do I evaluate h of negative 4? Easy cheesy. I'll go to h's rule that accepts inputs and rewrite it. Except everywhere h accepts an input, I won't put x, I'll put negative 4, my value for f of 0. So negative 4 goes there, and then we can simplify if possible. It looks like positive 4 divided by negative 4 overall is negative 1. I'm dying to know who had negative 1 already. Anybody have negative 1 already? Yes! Good job, you guys. You're doing great. Thank you. And we're 1 to go. Consider the domain now of a composition of functions h of g of x. And so we can do this a couple different ways. I think the easiest way, and allows us some practice with our composition of functions, is to find a simplified expression for h of g of x first. Then consider, right, our domain issues that we might have, if any, next. So we'll go ahead and go h of g of x. I'll rewrite that as h of, and then whatever g of x is. It looks like g of x is x squared minus 1. In order to get h of g of x function definition, I have to go to my function h and rewrite it. Except everywhere h accepts inputs, don't put x, put g of x in its entirety. Quantity x squared minus 1. So let's rewrite that. 4 over x squared minus 1. So what I want you to do now is go ahead and take a look at this expression. What concerns do we have when considering the domain of a particular function? Right? What are we worried about with domain? Well, what's one thing we're worried about? Go ahead and tell the class when I call on you. Heather? Good. We can't have a 0 in the denominator of a fraction because we can't divide by 0. There's no way to divide by 0, and so we can't have a 0 on the bottom of a fraction. So I like to take the quantity that's in the denominator right? If I have a fraction in my function definition, set it equal to 0 and see if there's any values of x that would create a 0 on the bottom of my fraction. So I'll take that x squared minus 1. I'll set it equal to 0 and say, are there any x values that would result in the creation of 0 on the bottom of the fraction? And for that, I can add 1 to both sides and solve by taking the positive and negative square root. Sometimes this reduces, sometimes it doesn't. In this case, the square root of 1 is just 1. Right? What squared equals 1 or 1? So I get two problem values, x equals positive 1 and x equals negative 1. When substituted into my function definition, we create a 0 on the bottom of a fraction, and that's not okay. But my final answer was, what's the domain? So we want to list that in set builder notation. So we'd say the domain then, the domain is the set of all x's such that x doesn't equal positive or negative 1. And that would be our final answer. That's pretty sweet. So did anybody find that 1 and negative 1 wouldn't work? Did we get all the way to the end of the last one? Okay, so that's the trickiest one. Good job. Because you have to do a composition first and then consider your domain questions. Aside from having a 0 on the bottom of a fraction, what other domain concern do we have? Raise your hand. So there's another domain concern we have. We haven't done much with it, but it's out there, lurking. Thanks, hands down. Margot?
A negative is
Right. It's not okay to have a negative number inside of the square root. We could have a negative in front of the square root. We just can't have a negative number inside of the square root. Excellent. Thank you. We'll run into that in the future. All right. First, let's take care of our assignment number 5. At this time, if you take out your assignment number 5, make sure that your name, 1A, and number 5 are clearly labeled as your heading on the top right. Please give yourself credit for those that you completed out of 11 in pencil, divide, enter, multiply by 4. And if you showed me your 8.2 and 8.3 reading questions, you're eligible for that 5th point. And we'll box your infinite campus score, honor to the nearest half point, nice and big, in pencil at the top of your page. What questions do you guys have about your infinite campus score today? Awesome, then let's go ahead and do pencils down. Let's get your accuracy fraction out of how many you did, about how many did you get correct. So pencils down, and let's switch over to our grading pens. So, in 1A, $20,240. B, $20,000. 2, the discount first, right? For any car priced X, if you take the discount first, the price will be 0.85X minus 3,000. But if you take the rebate first, the price then will be 0.85 times quantity X minus 3,000, or 0.85X minus 2550. Yes, the difference will always be $450. 3A is negative 21,296. B is negative 21,296. 4A is 35,152, and the same for B. 5, yes. That composition results in X minus 2. 6A, negative 28. B, 157. C, negative 52. And 6D, 133. 9A is a set of all real numbers except for 0. B, no. 10, the set of real numbers except for positive and negative 2. 11, the set of real numbers except for 0. 12, f of p is 0.8p. B, g of p is 1.05p, and you can get that by 1p, right? P plus 0.05p would be 1.05p. C, both give the same price because of the commutative property of multiplication. We're talking about commutative is just order doesn't matter, right? A plus b is the same as b plus a. C times d is the same as d times c. In 13, there was a mistake in the text that we fixed. G of f of x ends up being 0.6x minus 300. And that should do it for our bookwork. Go ahead and make sure that you have an accuracy fraction then out of the number you did. About how many did you get correct? circle it. Final check with your name, first and last. 1A, number 5, clear label. Infinite canvas score, box, and pencil. And then please pass from the back to the front, ladies and gentlemen. I appreciate your help. Front rowers, if you make sure they're facing the same direction, it'll make it much easier to record. So thank you. Everybody good with your number 5? Number 5? Purple pass, so I'm not bring it back to the foot. Okay, ladies and gentlemen, the final thing is our building functions worksheet and our rewriting formulas. Now, while these are 4 activity stamps, right, I just wanted to make sure that you had an opportunity to check your work. So we put answer keys, I put them on the back whiteboard and on the side whiteboard, a quick link. I think we don't need to spend much time on this because you guys did very well. We can check here, and we all got this stamp and this stamp. This rewriting formulas worksheet was the one that we didn't have as much time on. And so we want to make sure a couple of things. When solving, right? When solving an equation that involves a squaring, when you undo the squaring, please be attentive to detail. Make sure you're considering both the positive and negative square root. And so we saw that in several of these questions. Number 1 included a positive and negative square root. Number 2 did as well. And number 4 all on the first side. So don't forget that. And we talked about that a little bit together. And then on the back side, number 6. One of the areas of concern I saw in yesterday's B-Day classes and a couple of the A-Day students was when you go to solve for R in number 6. Everybody take a look. We're trying to solve for R. We're not quite ready to list our forward steps so that we can reverse and undo to get our solving steps. How come? In number 6, my R is the variable I want. It's right now in a quantity R squared in the bottom of a fraction. So I'm not ready to list my forward steps. Before you can list your forward steps, we need to get R out of the basement of my fraction. So my technique to get a variable out of the bottom of a fraction is to multiply both sides by that quantity. And that will move it up out of the basement of a fraction, and now I get FR squared on the left, or R squared F. Either way is fine. Equals M sub 1 times M sub 2. So once again, if you're trying to solve for a variable, you'll run into this in the future. Like on the quiz, you could see where your variable is originally on bottom. How do you get it out of the bottom? You multiply both sides by the quantity that contains it. Then you can start with the regular process. What questions do you guys have on number 6? Awesome. Then let's go ahead and get after our discussion today. By the end of today's class period, you're going to be able to find inverses of relations, and you'll be able to do it several different ways. We'll be able to do it given a list of ordered pairs. We'll be able to do it given a graph, and we'll be able to do it given a function rule, a formula. So 3 different ways you guys are going to be able to find inverses today. Lastly, we'll verify whether or not a given inverse relation is a function or not. Okay, and so we've got a big day today, and I'm excited to get going. First, we need to know then what an inverse is. And so we're talking about an inverse in mathematics as an inverse relation. So if you look up inverse in the dictionary, one definition reads to reverse in order. To reverse in order, to switch, to invert the position of something. Mathematically, the inverse of the inverse of a relation means to exchange the x and y in the ordered pair. So if we wanted to state the inverse of this given relation A, which contains the ordered pairs 3, negative 1, 5, 7, 4, 9, and negative 1, 5, it would be as easy as exchanging the x and y coordinate in each ordered pair. We don't change anybody's sign, right? We don't change anybody's sign. We simply reverse in order, right, those ordered pairs. So everybody, let's make the inverse relation. Let's call it A inverse. We'll get a new notation for this in just a minute. I'm going to call it A inverse, and I'm going to put a little -1 superscript there to denote that I'm finding the inverse of A. And so it's not an exponent. I'm not raising to the -1 power. It's just a notation that's read A inverse. It means the inverse of relation A. What would the inverse of relation A look like? It would be easy. All I would do was invert the order, right, of the coordinates in each ordered pair. So instead of 3, -1 being in the inverse relation, -1, comma 3 would be in the inverse relation. Instead of 5, 7, the inverse relation would contain 7, 5. What would the next ordered pair be? Brady?
9 and then 4.
9, 4. Thank you. What would the last ordered pair be? Katie?
5, -1.
5, -1. Good. Thank you. Notice how we didn't change anybody's signs. We're not changing positive or negative. We're not doing any fractions or reciprocals. All we're doing is we're inverting the position of each coordinate in each ordered pair. Now let's go ahead and graph the original ordered pairs. I'm going to do that in blue to match the color coordinates of my original relation A, and the inverses ordered pairs. I'll do that in green, and then we'll go ahead and consider the relationship between the two relations on the same XY coordinate plane. So carefully, let's plot those on your picture. We gave you coordinate axes now. I'm going to go ahead and graph relation A. It contains 3, -1, 5, 7, 4, 9, and -1, comma 5. On the same XY coordinate plane, please carefully plot the points contained in the inverse relation, A inverse. I'll do those in a different color. As you're finishing up your graph, go ahead and take a look at mine on the front smartboard and at yours at your desk, and then quietly talk with your partner about any symmetry, right? How would you describe any symmetry you see between the original relation A and its inverse, A inverse in green? Go ahead and talk with your partner now, please. Describe any symmetry. So how could we describe that symmetry between the original relation and its inverse? How could you describe that to someone else? Right? How could you describe that? Katie and Margot?
We said it was pretty much like a reflection.
A reflection? A reflection about what?
Like, the two images are like reflected.
Absolutely. Raise your hand if you had reflectional symmetry. Did anybody use the word reflection? Keep your hand up if you could see what you would reflect it about. And so would I reflect it across the x-axis? Would I reflect it across the y-axis? Kind of? Y equals x, that diagonal line, y equals x, that cuts through the origin at a 45-degree angle. Let's everybody go ahead and add a little dashed line through the origin. I'm going to use my line tool. So it turns out that our original relation and its inverse are mirror images of one another when reflected about the line y equals x. And so yes, we have reflectional symmetry about the line y equals x. Nice job. And y equals x is that diagonal line that cuts through the origin at a 45-degree angle. We can see that visually. Nice job, you guys. So reflectional symmetry about the line y equals x. Suppose f is a relation and g is the inverse of f. Then we've got several different properties that hold true. If a rule for f exists, a rule for g can be found by switching x and y in the rule for f. So that's exactly what we did to find the inverse relation. We switched x and y on every point. It's that easy. 2, the graph of g is the reflection image of the graph of f over the line with equation y equals x. And we just saw that visually in our last picture. To get a function's inverse graphically, we can simply reflect it over the line y equals x. And lastly, the domain of g is the range of f. And the range of g is the domain of f. What? Well, if we switched all the x's and y's to gain a relation's inverse, then it makes sense the set of values in the domain and range would also be switched. Because the original domain is all the x's, the original range is all the y's. If we flipped all the x's and y's, now the new relation, the inverse relation's domain is going to be the original y. And vice versa. That's pretty sweet. Let's go ahead and practice doing some sketches. So we've got a big page. We did landscape for you, right? So you have plenty of room. What we're going to do is practice taking the original relation in blue, and again, I'll do my inverse relation in green. But this time we don't have a collection of ordered pairs necessarily, right? We do have a collection of ordered pairs. It's just shown graphically. It's not as a list, but as an entire picture. So we've got a couple different ways we can do this. One thing that I like to do is grab onto integer points, key points x comma y, and then flip them just like we did before plotting points on the inverse relation. Then I also have a trick. After I've plotted those, I like to take the graph and I like to turn it kind of sideways so that I can do 2 left-right halves. And I'll show you how I do that with the smartboard. You can do it on your desk with your paper. First, let's get some key points. Everyone, we'll go ahead and pick out some key integer points in my original. If my original blue graph has the key point 2, 8, 2, 8, my new inverse relation will contain the point 8, 2. So everybody, let's do 8, 2. Right? 2, 8 is going to correspond to 8, 2 in the inverse relation. If my original graph contained the key point -1, 7, the relation, the inverse relation, will contain the key point 7, -1. Everybody, let's plot that. Is 9, 2? Thank you, Margot. 8, 2. There we go. Thank you. Much better. -3, 3. I think -3, 3 will be paired with 3, -3. All right, -3, 3 will be paired with 3, -3. I think we need some more. -2, 5 will be paired with 5, -2. And -4, 2 will be paired with 2, -4. Sorry, -4, 2. 2, -4. What are we missing? What are we missing? All right.
-4 is on 4
The -2 you did.
Yep, -2.
I know, but then you did
5.
+3. Oh, I don't
Your
know.
4,
That's
your -4, 2 is right now is 4, -2.
Ah, and it should be 2, -4. How's that? There we go, Luke. Thank you. All right. So what I'm going to do now is I'm going to group these. I'm going to group these so that I can spin it sideways and have a better chance of making a picture. So I'm going to go ahead and group these. And now I'm going to go ahead and take this and I'm going to rotate it. I'm going to rotate it so that I can have the best shot, right, of drawing a mirror image when reflected about that diagonal line. So if you turn your page, you don't have to do this, It just helps me do it. So if you turn your page on your desk, so you're looking at left-right halves, then it'll be easier for you to do the right-hand side, right? Because you left-right bilateral symmetry. So I'm going to go for it now. Looks like oh, easy there, shooter. So now I want to now we'll try. There we go. So now we can see we've got the mirror image when reflected about the line y equals x. Let's try another one. This one looks tricky too. So we've got lots of points here. Let's go ahead and grab some key ones to make our picture. So we'll see if we can't do a better job this time. It looks like I have a key point that's an intercept. 0, comma, and I'm going to say -5.5. 0, comma, -5.5. So I'm going to go -5.5, comma, 0. Two comma -6. I'm going to go -6 comma 2. -3 comma -7. I'm going to go -7 comma -3. Five -3. I'm going to go -3 5. The intercept 5.3 comma 0. I'll do 0 5.3. 6 comma 3. 3 comma 6. 7 comma 4. 4 comma 7. And I go off at 10 comma 5.5, so I'll go 5.5 comma 10. All right, let's see if we can't get this to work out a little bit better than last time. So again, I'm going to group. I'm going to spin. And I'm trying to do this just so I can get kind of mirror images, right? Mirror images. And now I'm going to go ahead and draw my inverse relation. I'm going to do it in green. Can we do it? I'm going to go for it. Hey, not too shabby. Much better. So we can determine the inverse relation graphically by reflecting the original image about the line y equals x. A mirror image of the original when reflected about the line y equals x, the diagonal, is the inverse relation. What questions do you guys have about our finding inverses graphically? So it's still finding ordered pairs and flipping the ordered pairs to plot. That still makes it easier for me. All right, now let's consider how we could find if the relation is a function or not. So let's consider the original in blue. Let's graph y equals 1/2 x squared. And we can do it the old school way by selecting some x values, plugging them into my function rule, and then producing the y coordinates before plotting each ordered pair x comma y. So let's go ahead and do that original in blue. Ready? If I plug in some x values, I'll do -2, -1, 0, 1, 2. I can generate some XY order pairs by evaluating my function rule for these X inputs. -2 squared, right? -2 squared is 4, and then half of 4 is 2. So it looks like this relation contains the point -2, comma 2. -1 squared is 1. Half of 1 is 1/2. 0 squared is 0. Half of 0 is still 0. 1 squared is 1. Half of 1 is 1/2. 2 squared is 4. And half of 4 is 2. So far we have several order pairs. I'm going to go ahead and add. I'm going to add the x value -4 and 4 so that I can get a bigger picture. Let's go ahead and add -4 to my x values. -4 squared is 16, and half of 16 is 8. 4 squared is 16, and half of 16 is 8. Now we've got plenty of order pairs to make a nice picture for my original relation, y equals 1/2 x squared. So here we go, -4, comma 8. -2, 2. -1, 1/2. 0, 0. 1, 1/2. 2, 2. And 4, 8. Everybody, let's carefully connect those in a nice smooth U shape. A nice smooth U shape for our parabola. We'll see this again next class period when we develop our parent functions before the quiz. On the same axis now, we're going to go ahead and graph the inverse relation. So how do I get an inverse? Well, if I'm given a list of values of ordered pairs, I can simply invert the coordinates. And so I'm going to go ahead and plot 8, comma, -4, 2, comma, -2, 0, comma, 0, 2, comma, 2, and 8, comma, 4. I'm going to go ahead and invert all those coordinates and sketch a graph of my new relation. I'll do that in red so that we can compare. 8, comma, -4. 2, comma, -2. 0, 0. 2, 2. 8, comma, 4. Oh. What ones did I do? 1/2, comma, -1. And 1/2, comma, 1. How's that? If we were now connect that in a nice smooth curve, all right, a nice smooth curve, what would it look like? It would look like the same thing, except turn to the side now. Okay? This is not a right side up opening parabola or U shape. It would be a parabola opening to the right hand side. Everybody see that? All right. Now consider the following questions. Is the original graph in blue a function? Is the original graph in blue a function? I don't know. Let's go ahead and do our vertical line test. And so recall, a vertical line test, right, allows us to take the original graph. I'm going to take my vertical line and I'm going to slide it across the original relation. As long as the vertical line crosses that original blue relation at most one time anywhere along it, it's guaranteed to be a function because no x value is paired with more than one output y value. It only crosses the blue picture once. So is the original blue graph a function? Tell your partner and be ready to share. Is the original blue one a function? Look, just be ready to share. I'll call on you. Logan, Barrett, is it a function? Yes. Yes, the original blue one is a function. Awesome. Awesome. Is the inverse a function? Go ahead and tell your partner. Is the inverse a function? All right. So what did you guys say about the red inverse relation? Was that a function? Aaron and Cody? No. No. Raise your hand if you had no. No. Good job. Why did you say no?
Because the clockwise.
Absolutely. A vertical line, when held up on the right side of the picture, right, crosses the relation more than one time, guaranteeing that a given input, in fact, you can see it right here, this input x equals 2 is paired with more than one output. In this first instance, it's paired with the output y coordinate -2. But right here, the same input x is paired with the output +2. So not a function because the inputs repeat. A given input value 2 is paired with more than one output. So not a function. Yep. Wow. Go with adjunct, extend the page there. So the inverse was not a function in this case. Sometimes it is. And so we're going to focus now on when a given inverse is also a function. So we're going to look back at our pictures again when we were talking about vertical line test on day 4. How can we tell if a given graph's inverse is a function or just a relation? So if I go ahead and do my quick scan, everybody find your pictures, we can do the original, yes, original, no, original, yes, a function. So let's go ahead and get that. The original, yes, top left, passes the vertical line test. Original, no, fails the vertical line test. The original graph in green, top right, yes, passes the vertical line test. Bottom left, original, yes, middle, no, last, no, so we've got a yes, no, no. Okay, so if we perform the vertical line test on an original relation to determine whether or not it is a function or not, and we're going to flip all the x's and y's, we can now perform not the vertical line test on the original, but the horizontal line test on the original to determine if the original's inverse will itself be a function. So what I'm going to do is take this line, and I'm now going to use a horizontal line on the original. I'll do the opposite test on the original to determine if the inverse will be a function or not. So do we think the inverse of the original will be a function? No, it fails the horizontal line test, guaranteeing its inverse will not be a function. So we've got a no. Take a look at the top middle. Does the top middle pass the horizontal line test? It does. If the original passes the horizontal, its inverse is guaranteed to be a function. So we've got a yes. Top right. Does the original pass the horizontal line test? No, it fails it dismally. In fact, the horizontal line here crosses the picture more than 3 times. It passes 4 times here. So no, its inverse will not be a function. Go ahead and decide with your partner on your own, right, at your desks. Go ahead and determine if the original will be a function. I'm sorry, if the original's inverse will be a function. Be ready to share.
Yes.
Yes.
Okay, what'd you guys come up with? Carson and Dakota.
Yes.
Keep going. Raise your hand if you had yes, no, no for is the inverse a function. Yes, no, no is correct. The original failed the horizontal line test in the last 2, guaranteeing that the original's inverse will not be a function. However, in the bottom left, the original passed both the vertical and the horizontal line test, guaranteeing that not only the original is a function, but its inverse will also be a function. Such a function is special and called one-to-one, and we'll deal with that in FST. But for now, when is the inverse of a function also a function? If the original graph passes the horizontal line test, then the inverse of the original graph is a function. We still use the same old vertical line test to tell whether or not the given relation is or is not a function. But if I want to know if the inverse of the original is a function, I can use the horizontal line test on the original. Okay. Our final topic of discussion involves properties of inverse relations and functions. And we're going to go ahead and determine how to find the inverse relation now using an equation. And we'll be able to verify that two relations are indeed inverses or not. So here we go. Remember, an inverse will always switch the input x and the output y. So if the original function included pairings like r comma s, the inverse relation would include pairings like s comma r. We can say an inverse will undo a function. We'll be using f inverse to represent the inverse of x. And so this notation right here with that little f and then -1 superscript of x, that is read f inverse of x. It does not mean an exponent. It's not raising to the -1 power. It's not a reciprocal. It's not a flipping of a fraction. It's just read f inverse as the notation. So if f is a relation and g is the inverse of f, we already talked about these three things from before, but we wanted to make sure that you got it on a printout. And so we included this on your printout now. We can switch our x and y in the original to get the inverse. We can reflect the original about the line y equals x to get the inverse. And the domain of the original corresponds exactly to the range of the inverse and vice versa. Let's go ahead and find now some functions that are more complex. Let's find their inverse. So we've done it graphically by reflecting. We've done it with ordered pairs by inverting coordinates. Now we're going to do it with an equation. Everybody consider the graph the function f of x equals 6 plus 3x over 5. We're going to find the inverse algebraically. And to do this, we'll still invert x and y. It's just now we're not inverting x and y in a point, right? Or on a graph, we're inverting x and y in equation. So the first thing we do is rewrite the statement using y. Recall that y equals f of x. So I'll simply rewrite my original as y equals, bless you, 6 plus 3x all over 5. Now comes the inverse step. After rewriting the original with x's and y's, I will interchange the x and the y. Here comes the inverse part. We're going to invert the position of x and y in my original. So everybody, rewrite your original y equals 6 plus 3x all over 5 as x equals 6 plus 3y all over 5. So you rewrite the original, but you switch the position of x and y. Now we solve for the new y, and lastly call that new y f inverse of x. So let's go ahead and solve for the new y. I'll go ahead and multiply both sides by 5 to clear the fraction. This produces 5x equals 6 plus 3y. Now I'll go ahead and subtract 6 from both sides to get my y term alone on one side of the equation, everything else on the other. So I get 5x minus 6 equals 3y. And go ahead and tell the class how I can get this y alone when I call on you. What will I do to finish this out? Marina?
Divide by 3.
Thank you. I'll divide both sides by 3 to get y alone. So y equals 5x minus 6 all over 3. And I'll replace that new y with f inverse of x in accordance with my proper notation. So if y equals 5x minus 6 all over 3, then f inverse of x equals 5x minus 6 all over 3. We started with an original, right? We rewrote with x's and y's. We interchanged the position of x and y in my equation. We flipped them in my equation, solved for the new y, and then renamed it f inverse of x. What I want to do is show us graphically how these appear on the xy coordinate plane. Okay, So on my emulator, we're going to go ahead and enter my original function. I'll do that in blue. So that was quantity 6 plus 3x, close quantity all over 5. And then I'll enter my, oh, that's not going to be pretty. And then I'll enter my inverse relation that we found. That was f inverse equals quantity 5x minus 6, close quantity all over 3. Notice how I'm using parentheses around my numerator, right? Because we want the whole thing to be divided by the denominator, not just the last thing, not just the 3x and not just the 6. After entering those in my grapher, I'm going to go ahead and zoom square the 5th option to correct for the fact that my window is a rectangle. I want to make it appear to be a square graph. And then I'm going to press enter, and voila, there's my original in blue. Here's my inverse in red. And here is that reflectional line, y equals x. I'll add that to my picture too. And it should cut them right in the middle. Do you guys see that? It's cutting them right in the middle. So they are mirror images of one another about the line y equals x when reflected. That's pretty sweet. Awesome. So, pretty sweet. That's pretty sweet, I guess you could say. Awesome. All right, let's go ahead and find the inverse of the following function. So everybody, let's practice with our 4-step process. Be ready to tell the class, right, what the next step is when I call on you. So have your steps ready, because I'm going to call on you. Let's go ahead and find the inverse of the given function. What's my first step in the 4-step process? Tyler?
You substitute y for f.
Absolutely, thank you. So you'll rewrite the original with y in place of f of x. So y equals 2x minus 8. Thank you. Go ahead and tell the whole class what step 2 is when I call on you. So what's my step 2? Katie? Absolutely. So here's where we get the inverse. We're going to interchange the position of x and y in my equation. Instead of y equals 2x minus 8, it'll be x equals 2y minus 8. Good. What's my third step then? Go ahead and tell the class. Dakota? Get y by itself. We're going to solve for the new y. So here's my new y. We need to solve for that new y to figure out what the inverse is. So I'll add 8 to both sides. So I'm going to do plus 8, and I get x plus 8 equals 2y. Divide both sides by 2. So I get x plus 8 all over 2 equals y. And then step 4, my last step, what do I have to do? Luke?
Change it to f minus 1.
Good. We'll rewrite that new y as f inverse of x. And that is equal to x plus 8 all over 2. So here's my inverse. Now Julie thinks the inverse is given by 1/2 x plus 8. And we got x plus 8 all over 2. What did Julie likely do to get her incorrect answer? Besides not paying attention in class. That's so mean. Oh my gosh, that's so mean. She could have done a couple things, right? So go ahead and tell your partner what's something she could have done.
Or she just did
Okay, I see at least 2 things she could have done that are plausible for her mistake. I mean, she's wrong, but there's a couple ways she could have gotten there. So what's one thing she could have done? Katie?
She could have, well, she divided by 2 on x, but not 8.
So if she had gotten to here and simplified this, she could have applied that dividing by 2 to the x, but not the 8, and gotten 1/2 x plus 8. Good. What's a different way she could have gotten here? What's a different way? Thank you. What's a different way she could have gotten there? Ben,
to the power of -1.
so
Like 2 and then the -1 above.
oh, so inverting 2 and making 1/2?
Yeah.
So she could have raised it to the -1 power and gotten 1/2. So 2 to the -1 is flipping it and gotten 1/2, so reciprocal. So she could have taken the reciprocal, okay? And then that 8, right? She could have undid the subtract 8 by adding 8, right? So she just did 2 inverse things, right, to the original and tried to make the inverse like that, but order matters, and so she can't just do that. Well, this is an important point. So we want to make sure that we're following our 4-step process and not just guessing at the inverse, but actually doing the procedure. Nice job. Thank you guys for sharing. So let's go ahead and take my originals. Where are they? Let's go ahead and take my originals. And let's perform a function composition with a given value. So we're going to do f of f inverse of 10 with our function. So here we go. F of f inverse of 10 says find f of, and then f inverse of 10 would be going to my f inverse rule, which takes inputs and putting a 10 in everywhere except inputs. So this would become f of 10 over 2 is 5, right? 5 plus 4 is 9. So I'm getting 9. So I plugged in 10 into f inverse. Everywhere I see an x, 10 divided by 2 is 5, 5 plus 4 is 9, and now I'll evaluate my outer function, the rule f. Everywhere I see an x, I'll put a 9. So I'm going to 2 times 9 is 18, minus 8, I'm getting 10. Right, I got 10. Now, let's do f inverse of f of 7. So f inverse of f of 7. So let's go ahead and do f inverse of, and f of 7 would be go to f's rule and replace my input with 7. That would give me 2 times 7 is 14. 14 minus 8 is 6. So I'm getting 6 for f of 7. And lastly, that would be f inverse of 6 over 2 plus 4. And that's 3 plus 4. And that's 7. Go ahead and tell your partner what you notice about these two function evaluations. So, what did you and your partner notice about these two compositions, all right, about these two separate compositions? Taylor and Mark?
The 2 input values that they gave us were the value that we ended up getting because like they're inverse of each other.
Yeah, the input value in the first one was x equals 10. We evaluated my inverse function at x equals 10, took the intermediate value, plugged it into my outer function, the original, and I produced 10. In the second function composition, I put in an x value of 7 into the original. I evaluated the inverse, right, the inverse function now at that intermediate value, and I got 7 right back out. And so it turns out that a function and its inverse, right, are, well, inverses. Whatever one does to a given input value, the other one will go back and undo it. I can stick 7 into my first machine, and when I plug the intermediate value into the inverse, it'll turn it right back into a 7. When I plug 10, the input value, into my function machine and got an intermediate, plugging that into the inverse will undo whatever was done and get you right back to your original input value. And so the composition of a function in its inverse, right, will always undo the original and get back to the very beginning. Okay, we're going to generalize that in the next set. Margot.
So if we have like a question like this on the quiz, do we have to show all our work when we got to 7? Like do we have to write it all out, or can we just say they can't say it?
Only if they're inverses of one another.
Yeah.
Right? Only if they're inverses of one another. So,
Do we have to show all our work if they're inverses? Do we have to write all that out?
if they're inverses and you're told that they are, then no. Okay? If you're asked to verify algebraically, then yes, because then I want to see. Let's go ahead and take a look at now the generalized form. So once again, we've got our functions. And let's find the composition f of f inverse of x algebraically. Here we go. I'll go to my outer function f, and I'll plug in f inverse of x everywhere it accepts inputs. So after substituting f inverse of x into f, I'll distribute. 2 times x over 2 is just x. 2 times positive 4 is plus 8. And then I still have the minus 8 chilling on the backside. Combine like terms, and what do I get? I get x. Consider the reverse composition. That is, plug f's rule into f inverse's function rule. So f inverse is going to accept 2x minus 8 everywhere f inverse accepts inputs. F inverse happens to accept inputs on top of that fraction, input divided by 2, and then plus 4 in the end. And now we can go ahead and reduce. In the fraction, 2x minus 8 all over 2, what quantity on top is being divided by 2? The x term or the 8 term? Both. That's why we have the fraction bar that's along there. And so if I want to break this up, this would be 2x divided by 2 is 1x. Minus 8 divided by 2 is minus 4. And then I still have plus 4 chilling on the backside, which means that, lo and behold, either order, right? Either order of composition of a function and its inverse results in the original input x. There's my generalized composition. If x goes into f inverse, whatever f inverse did to that input, f will undo it and get you right back where you started. If input x goes into f first, whatever my function rule f does to it, f inverse is going to undo that and get you right back where you started. So we can generalize this as follows. Looking at the previous slide, if function g is the inverse of function f, then f of g of x equals what? If g is the inverse function of f, then g of f of x equals what? Well, we just replace those with g's, right? So what does f of g of x equal? X. What does g of f of x equal? X. And that will be my algebraic test to verify that two functions are indeed inverses of one another. All right, important facts to remember. We'll be using f inverse to represent the inverse of f of x. The domain of f becomes the range of f inverse. The range of f becomes the domain of f inverse. F inverse of x will always undo f of x. And the composition f of f inverse of x is the same as the composition f inverse of f of x, which gives us our original input x right back. Awesome. So let's go ahead and write down a response for each of these. How do you find the inverse of a relation if you're given ordered pairs? How do you find the inverse when you're given a graph? How do you find the inverse when you're given an equation? So 3 different ways we found inverses today. The composition of two inverse functions, f of f inverse of x gives what? And then what graphical test is performed on the original graph to determine if the original graph's inverse is a function. Let's go ahead and write down a response for each of these. Please be ready to share on the smartboard your answers to the points of today. Okay, let's go ahead and share responses then with the whole class. And so, how do we find the inverse of a relation if we're given ordered pairs? What is it that we can do procedurally? Go ahead and tell the class. Braden?
You can switch the x, y pair.
Absolutely. We can switch the x and y in each ordered pair to get the inverse relation. What about if you're given a graph? Right? So what can you do if you're given a graph? Jackson? Yeah, we can take that original and reflect it over the line y equals x. Absolutely. Good job. What happens if we're given an equation? So what do you do to find the inverse of a relation when given an equation? Cody?
Switch the x and y to swap them down, and then put x, x.
Absolutely. So we'll rewrite the original with x's and y's, switch the x and y in the equation, solve for the new y, and call it f inverse. So that's a 4-step process. Good job. The composition of two inverse functions, right? The composition of two inverse functions always gives the same result. What is that result? Eric? X, absolutely. Thank you. And what graphical test is performed on the original graph to determine if the original graph's inverse will be a function or not? So what test can I do on the original to determine if the original's inverse will be a function or not? Casey?
The horizontal line test.
The horizontal line test is correct. Nice job, you guys, and thank you for sharing. You did great work today. What questions do you have about our inverse relations? And today we will have an opportunity to work on assignment number 6. I just want to point out that there'll be a quiz, right? A reminder, there'll be a quiz next class. And you've got some resources. So what do you have at your disposal? You've got the practice quiz with workout solutions. You've got bell work solving equations like yesterday's class had a great example with multiple steps. Also, on the Advanced Algebra Workshop Moodle, there's a practice quiz that you could go and complete if you wanted to get an idea of the format. Again, you don't need a username or a password. You could simply go to the district, the high school webpage, click on the Moodle button, math, and then Advanced Algebra Workshop has a practice quiz up that you could do it. Again, it's not an assignment, it's just if you want extra practice. Thanks for using this time for Advanced Algebra, and for the first time, no reading questions for next class. No reading questions for the next class, but 2 book sections. You can use this time to work quietly, and you may work with another person so long as it's quiet today. Nice job. Mark? Okay, so let me go ahead and close out the recording then. You guys did great.